Hello, welcome to Easy Math. My name is Zishan, and we are doing proofs by mathematical induction from IBHLAA Math. And in the first video, we have already discussed questions from PMI which involve divisibility. Today, we're going to do questions from PMI which involve inequalities, and let's go do some questions which have appeared in the past year papers, and then we're going to give you some to do after you've watched the videos. You may be able to solve all of them. If you're not able to do all of them after watching the video, you're going to have to tell me. I will create more videos explaining these kind, and that's how we will cover this topic. For now, let's go do some nice questions from inequalities and PMI. These are the ones that I've already shown. So yes, this is the first one. Solve the inequality this and use mathematical induction to prove that this is always equal to this is always greater than n square. This is always greater than n square for n greater than equal to 3 for 7 marks, where the first inequality was 2 marks. Well, this is something that you have already done in AdMath. I don't want to solve this one. I'll simply go tell you what the answer is for this one. This is supposed to be uh, x lying between 1 plus root 2 and 1 minus root 2 will be your solution for the part A. Okay, so we now know that x square is greater than 2x plus 1 for all x which is between, sorry, I think there needs to be a greater than here, greater than this and lesser than that. Now that's a better thing to write there. Yes. So you go x greater than 1 plus root 2 and x lesser than 1 minus root 2 is when x square is greater than 2x plus 1. That is our solution for the part A. Now we're going to do the part B. And again, same situation like we did in the first video. We check for the base case where n is supposed to be 3. In this set, the smallest number is a 3. We'll check. 2 to the power of n plus 1 comes out to be 2 to the power of 3 plus 1, which is a 16. That is the 2 to the power of n plus 1 part comes out to be a 16 when n is a 3. And let's look at n square. That's a 3 square and it's a 9. And of course, 2 to the power of n plus 1 is greater than n square. 16 is greater than 9 when n is a 3. So base case, it's true for the base case. That is your part 1, step number 1. Now we go do the step number 2. Okay. Step number 2 is your hypotheses. Like I told you, inductive hypotheses. Let's assume 2 to the power of n plus 1 is greater than n square for n equal to k, or 2 to the power of k plus 1 is greater than k square. That is your inductive hypothesis. Keep this equation, it will help us. And now we go do the actual proof where we are like, we have to prove for n equal to k plus 1, 2 to the power of k plus 2 is greater than k plus 1 whole square. What do I do here? Well, in the expression out there, I substitute a k plus 1 in place of n. When I do that, I end up with a 2 to power of k plus 2. And on the right, I'm going to end up with a k plus 1 whole square. Okay, fine. Well, this is what I want to prove. And this is what I've already assumed to be true. Well, let's bring this here. Equation number 1 from the inductive hypotheses. I already know that 2 to the power of k plus 1 is greater than k squared. Let's multiply both the sides by a 2. What do I come to? 2 into 2 to the power of k plus 1 is greater than 2k square, or 2 to the power of k plus 2 is greater than 2k square. Okay, that's a truth which comes from my inductive hypotheses, but that's not what I want. I want this when I have that. What is it? This should be greater than this, and this is greater than that. Okay, so let me open up a new blank page, and from there we'll go. And yes, and now comes the most critical step in the solution. This is what I want to prove. And this, from my inductive hypotheses, is something I have come to know. This is greater than that, and the same thing is greater than 2k square. Well, if I go prove that 2k square is always greater than k plus 1 whole square, that concludes my solution that this will always be greater than that. If I can prove that the right side is always greater than the right side here, of course, this will by default be greater than k plus 1 whole square. Okay. What is the idea behind here? See, if I want to prove A is greater than B, and I already know A is greater than C, all I want to prove is that C is always greater than B. If C is always greater than B, these two together simply support A is greater than B. Okay, so that is what we are supposed to do. I'll say it again. If I know that A is greater, if I want to prove A is greater than B, and I know A is greater than C, all I want to prove is that C is greater than B, which makes this a truth by default. Okay, so that's what I'm going to do. So let's compare in my solution 2k square and k plus 1 whole square. Okay, to prove 2k square is greater than k plus 1 whole square, or 2k square is greater than k square plus 2k plus 1, or k square, if I take everything to the left, k square minus 2k minus 1 is greater than 0. Okay, so I have simplified this to look like that now. Question is this always true? Okay, let's see. Well, if you go to the first part of this question, you have already proven that x square is greater than 2x plus 1, x square is greater than 2x plus 1, or x square minus 2x minus 1 is greater than 0 for x greater than 1 plus root 2 and lesser than 1 minus root 2. You have already proven that this is greater than 0 for this set of values of x. Okay, what does that mean? It means this should be greater than 0 for k greater than 1 plus root 2 and lesser than 1 minus root 2. Question is, k we have assumed to be equal to equal to n, and n was always greater than equal to 3. In our question, it said n should be greater than equal to 3. Okay, is, is this greater than 3? No, it is not. So, for k greater than 1 plus root 2, this is always greater than 0, and this is about 2.4142. So, of course, this is true for k greater than 3. If it's true for k greater than 2.4142, it should be true for k greater than 3. So, now you go tell them, let me delete all of this, which is always true for k greater than 1 plus root 2. This is from the part A of the question. Or k square minus 2k minus 1 is greater than 0 for k greater than 3. Or 2k square is greater than k plus 1 whole square for k greater than 3. And that is how you come to a conclusion. And hence, 2 to the power of k plus 2 is greater than k plus 1 whole square for k greater than 3. And now you conclude, you tell them, like you did in the first video. Um, Base case was correct. Assumed It's true for n equal to k. This also comes out to be true. So it should be true for all n greater than equal to 3. That's how you do it. Okay. So the only comparison thing with inequalities is what you know and what you want to prove. There should be a comparison between the right side of what you know and the right side of what you want to prove. There it is. And using this, I come to a conclusion where it's actually always true. This thing is always true. Okay, greater than 3. That's how you go about this kind of question. We'll go do one more. Okay, now let's look at this one. Show that this is always equal to this, where for n greater than equal to 0. Well, I don't want to do this one. Again, it's a very easy thing. You only want to rationalize the thing on the left. You start from the left, 1 by root of n plus root of n plus 1, divide and multiply by root of n plus 1 minus root n, and a root of n plus 1 minus root n. You will end up with this on the right for 2 marks. Okay, that was the rationalization bit. Nothing there. Hence, show that root 2 minus 1 is always lesser than 1 by root 2. Well, root 2 minus 1 comes out to be 1 by root of 1 plus root 2. And that's a 1 by 1 plus root 2. Of course, 1 by 1 plus root 2 is always going to be lesser than 1 by root 2. Why? Because this is always greater than that. 1 divided by a larger number, 1 plus 1 by root 1 plus root 2 will always be smaller than 1 by root 2. That's our proof. That's 2 marks. Okay. So from the part 1, we used this is equal to that. And then I got to this thing, which of course is always lesser than 1 by root 2. So that was 2 marks again. Okay, now let's go do the third bit. Prove by mathematical induction that this is always greater than root n. Well, first you want to understand what this means. Okay, so I'm going to go take this and a blank page and I'll expand this for you to understand what this actually means. Let's see. Okay, so if you have summation of that's what you read. That's known as the sigma function. You read it as summation of 1 by root r starting from r equal to 1 to rn. What is that? The compressed form of, well, it is 1 divided by root 1 plus 1 divided by root 2 plus 1 divided by root 3 till you reach 1 divided by root n. That's what it means. So writing this whole thing in math, we use the summation function or the sigma function to denote that. That's the sum of all these terms starting from a 1 out there and a n. So you write start from a 1, go to a n, add all 1 by root r terms. That's what it means. Okay, so in our question there, this was to be proven. Well, sometimes you may have it look like that. That also means you want to start from a r equal to 1 and move on to a n, adding them all like that. Okay. And in our question there, we had to prove that this is always greater than root n or something. Let me just check once. Is always greater than root n. Okay. This is always greater than root n for n greater than equal to 2. Okay. That is what you want to prove. Hmm. Hmm. So let's go do it again. We do the inductive step, inductive hypotheses. I'll prove that this is true for n equal to k. So 1 by 1, 1 by root 2, 1 by root 3 plus 1 by root k is greater than root k. That's a truth that I've assumed to be true. And now I want to prove that it's correct for n equal to k plus 1. So you want to start in the expression here from n equal to 1 and reach a k plus 1 here, and it should come out to be greater than root of k plus 1. Okay, fine. Well, I bring back my inductive hypotheses in here, and in that step, I add a 1 by root of k plus 1 on the left and on the right. So this is a truth that I know from my inductive hypotheses. But this is not what I want to prove. I actually want to prove this, and I know this from my inductive step. And again, what do I do? Well, I compare the right side here with the right side there. If this is always greater than that, my job is done. Okay, let's assume it's true. Now, to prove that this, the thing on the right here, is always greater than that, the thing on the right there. So, okay, I go root k plus 1 by root k plus 1 is always greater than root of k plus 1. I take this to the other side. Root of k plus 1 onto the other side comes out to be a root k minus root of k plus 1 is uh, lesser than 1 by root of k plus 1. Why did I flip the inequality? Remember, there's an intermediate step. Root k minus a root k plus 1 is greater than minus 1 by root of k plus 1. When I go multiply both the sides by a minus 1, the inequality has to flip. Okay, so the inequality has to flip. There it is. Multiply both the sides by a minus 1, this by a minus 1, and that by a minus 1. What do you end up with? Well, you end up with, let's write that again. I think I wrote it wrong the first time, so we're going to go write it again. Multiply the left side by a minus 1, you end up with a root of k plus 1 minus a root of k, and it's lesser than 1 by root of k plus 1. And from my part 1 of the question, I already know root of k plus 1 minus root k is equal to 1 by root k plus root of k plus 1. So that's what I'm going to do. I'm going to replace this with 1 by root of k plus 1 plus a root k. And it should be lesser than this, which is actually always true. Look at that. 1 by root of k plus 1 plus a root k and a 1 by root of k plus 1. There is an added term of root k out there in the denominator on the left. Of course, this guy is going to be lesser than that because this part, the denominator here, is larger than the denominator on the right. Okay. So you go, this is always true. So what does that mean? It means summation of r equal to 1 till a n 1 by root r is greater than root r for n equal to k plus 1. The right side here came out to be larger than the right side there, which means the thing that you want to prove is actually correct. And now you go conclude it. You're like, oh, for n equal to 3, it was n equal to 2, it was correct. That's where we proved that this thing is greater than, that's the base case. If I have not done it, you can also do it. You'll see that it comes out to be true for n equal to 2. And then assuming it's true for n equal to k, it comes out to be true for k plus 1. And that is how you conclude this solution again. So again, the thing was, if A is supposed to be greater than B, if this is what you want to prove, and A is already greater than C, you only want to compare the C with the B. And if C comes out to be larger than B, and if C comes out to be larger than B, your job is done. Again, so that was us one other question you want to do. There are many more of these. Wait a second. Okay, so now I'll show you some questions you would want to do. Well, take a screenshot, this one, and then you want to do this, 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 and this. So what is it? I'll show it to you again. You take a screenshot, okay? You go question number 2, 3, 4, 5, and 6. If you end up doing these questions, uh, you are fine with inequalities. There are some more questions you would want to practice, but that is only after you are able to do these, okay? Do let me know if the video was any help solving these. If it's not any help or it doesn't help, you tell me. I'll I'll create a better video out of it. Okay. That's it for today. Take a screenshot and I'll see you soon. Bye bye.